Tracy.
Good morning.
Should we wait for the others or proceed? I think we should wait.
Oh, okay. I have somewhere to be.
Oh, okay.
It's all recorded, yeah?
Yeah, it's all recorded. So yeah, I think you start the catch up from the YouTube video.
Okay, I could wait till like 10, up to 10:05. Yeah.
Okay.
Okay, Godwin,
Yes,
I think I'll start. Is that okay?
that's okay.
Can you see my screen?
Yeah.
Okay, so today I wanted to look into the addition rule. The addition rule as written below is just a way of combining different probabilities. So in the addition rule, we calculate the probability of at least one or multiple events occurring. It bases off the principle of combining probabilities while accounting for any overlap between the events. So sometimes we have an intersection between events. The addition rule helps us prevent repetitions. So if we had a group of people who eat different cuisines of food, but some ate both the same kind of food, we don't want to count them twice. I wrote a note to remember mutually exclusive and non-mutually exclusive events. Mutually exclusive events cannot happen at the same time. If you roll a dice once, you can't get one and two at the same time. You get one of them at that go. That is what they mean by being mutually exclusive. Then non-mutually exclusive can occur simultaneously. If I had a deck of cards and I picked one card from that deck, there's a possibility of me getting hearts, which is a king. So those two events can occur simultaneously. So they are non-mutually exclusive. A compound event under the addition rule. This is an event which joins two or more simple events. It involves the occurrence of two or more events either simultaneously or alternatively. Compound events can be mutually exclusive, non-mutually exclusive, independent, and dependent. Independent means the occurrence of one probability does not affect the occurrence of another. So within compound events, the addition rule specifically addresses the event involving or. So an example given below, probability of rolling 1 or 5 on a die. Now this is mutually exclusive because they can't happen at the same time if you roll the die only once. So you either roll one or the other, or if you're rolling it twice, you can roll both. A or B is equal to the probability of A occurring or B occurring or both A and B occurring in a simple trial. Then I have an example of court cases. If you consider court cases, we have people that are tried for being guilty, those who come off not guilty. So some people who get tried for guilty actually committed the crime. That's why I wrote did it. Then those who did not do it, this did not do it, but they come out of the court session as guilty. Then these ones actually did it and they are tried guilty. We also have not guilty, and the number of people who are not guilty and actually did not do it, 85. The number of people who were tried not guilty but actually did it, and 9. So you see false positive, true negative, true positive. Let's explain it below. So true positive, predicted guilty and actually did it. That means the trying was correct. It is a true positive. A false positive, predicted guilty but did not do it. They were looking to find that the person was guilty and they did, but it is false, they did not. That's why it's a false positive. Then the opposite for the others. True negative, you found not guilty and you did not do it. So on the negative end, the trying was true. False negative, predicted not guilty but did it. So we can use the example above to find different probabilities within the addition rule. For example, how many people are guilty or did it? So if we go back to the table, guilty, and they have to be either guilty or did it. That means we have for guilty, the 11 that are guilty and did not do it, the 72 that are guilty and did it. Within the did it, we have 72 that are guilty and did it, and 9 that are not guilty but did it. So you see the 72 appears twice. Within the addition rule, we try to eliminate that. So we are going to have 11 plus 72 counted once because they're the same people, plus 9, which is equal to 92. To find the probability, you get this number for the event out of the total number of people there. So event out of total sample space. Then required elimination of any double count. With statistics, we're always trying to narrow down to the most correct answer. We do not want to count people more than once, even though they lie in more than one category. They're still one individual. So probability of A or B will be equal to the probability of A plus probability of B minus the probability of them occurring together, because that would be a repeated count. So the AND represents occurring at the same time during a single trial. Then disjoint events, these ones are separate, they are independent. So I wrote events which are mutually exclusive cannot happen at the same time, like pulling out a card from a deck of cards. You cannot pick a hat and a club at the same time. So an example, a Venn diagram showing disjoint sets. The Venn diagram below shows disjoint sets. For example, rolling a die once, you can get only one number showing the upper face, nothing more. So probability of A and probability of B are completely different. An example, this is still all under the addition rule. The probability of selecting a hat or a spade in a deck of cards. So probability of a hat or spade will equal to probability of a hat plus probability of a spade minus the probability that they will both occur. That is, there's 13 hats in a deck and 13 clubs, and there's no club and hat card. That is why probability of hat and spade is 0. But you understand, I hope you understand the logic. Could I get some feedback?
Yes, yes, I'm following and understanding.
Uh, Someone joined, yeah?
Yeah, Ian joined.
Hello, Ian. Okay.
Hello, Tracy.
I was talking on the addition rule today, adding different events together without having to have repetitions, like one event being counted twice. So I looked at compound events and disjoint events today. And I've tried to keep it within the 10 minutes that I am given. Last time I went a bit overboard. All right,
All right.
that's what
Thank you. I joined a little late, but let's catch up with
still presenting.
time.
Okay, my time is up. I think you can carry on. I'm sorry I have to go. I have another engagement now, but I'll watch from the YouTube video. Thank you for your time.
Thank you for presenting. Ian,
Yes, yes, good day.
yeah, if you had prepared something, I think it's okay. You can present. Unfortunately, this week unfortunately this week
All right.
I wasn't able to prepare.
All right. Let me present what I had last week. Can you hear the background noise in my environment?
It's not it's not very significant, but I can clearly get what you're saying.
Okay. Let me log in with my computer and share my screen.
Okay. All okay? I'm not seeing your shared screen.
Oh, I was still logging in with the computer.
Okay.
Godwin, you can see the screen.
Yes.
All right, let me share in a few minutes. Okay, last week we covered, I didn't cover the control not get because of network, but I can do up it now. So the control not gate is one of the gates in quantum computing, similar to the gates we covered last week. We looked at the NOT gate, and we saw that the NOT gate flips the qubit state. So if you have a state 0, it turns it to state 1. Then we looked at the Hadamard gate. And so today we're looking at a controlled NOT gate. It's also abbreviated as CNOT. So we now know a level of universal quantum computing. We have dealt with single qubits, but we need a way for qubits to interact with one another. That is
Someone's
2 or more
presenting and
qubits.
I have to
So
leave.
we're looking at a single qubit system now. We're trying to see how other qubits can correlate. So the CNOT gate creates an entanglement state in quantum computing, which is very important. Last week I told you about entanglement, and we looked at the definition from the internet. And well, here I want to get a brief definition from the internet, and they say entanglement is when two particles, such as a pair of photons or electrons, become entangled. They remain connected even when they are separated by vast distances. So that's what we mean by entanglement. So entanglement is very important in quantum computing. And how do we create this state? We create this state using this gate. So
Yeah, your audio has gone off.
Sorry about that.
Nice.
So we have the four computational basis states corresponding to a 2-bit system. So what does this mean? We're looking at 4 computational basis states. So we have these A, B, C, and D. All these are states. But what you need to understand is that what A means, I'm supposed to represent this as alpha, beta, gamma, and so on, and those represent the complex amplitudes. And what they mean is you can represent a qubit in a complex state. So there are 4 states, okay, and this is a superposition. So a qubit could be in this state. This is a superposition. And then we have a 2-bit system. We can see we have this. Remember, previously we're dealing with Ket 0, Ket 1, and so on. But this time we're dealing with Ket 0, 0, Ket 0, 1, Ket 1, 0. And that's what a 2-bit system means. So how does it work? So the CNOT gate in this here they're saying the first is the control qubit, then the second is the target qubit. And so it flips the target if the control is set to 1. So what does that mean? When we look at this diagram here, this is the representation of the CNOT gate, and here we have this black spot represents the control qubit, then this is the target. And they're saying if the control qubit is 1, it flips the target, and we're going to see how that works. Okay, so we've seen this is the control and this is the target. Okay, so here we have a mechanism. We have the control qubit, and I'm going to call it X, and then the target Y. So this was before, these 2 columns, that was before. So when the state was 0, the target was 0. When the state was 0, the state was 1 here. Okay, so all this happened before. Okay, and then when we look at this state, we have 1, 0, 1, 1. So when the control qubit was 0, the target remains 0. Okay, you can see the target is 0. Here it's also 0. When the control is 0, the target is 1. And then we see the target is remaining the same. We look at this control qubit as 1, the target is 0, it changed it to 1. So the difference is here. The difference is here. We can see that. So that's the mechanism, okay? And then when we just go back to this diagram here, when we look at this diagram, we have this state, okay? I remember I talked about the 2-bit system. We have 0, 0, 0, 1, and 1, 0, and 1, 1. So we have the target as 0. We have the target here as 1, and we can see that they're unchanged. And then here where we have 1, we can see that the
Yeah, and I think your microphone has gone off again. Ian, your audio has gone off again.
Hello, Godwin.
Hello?
Oh, sorry about that.
It's okay.
Um, okay, let me share my screen. Okay, so yeah, I was still talking about this two-bit system, and we're looking at the first digit being the control bit, and whenever it's one, it flips the other state. Yeah, so that's basically how it works. Um, so moving on to the next slide, we have the equation. Uh, this equation tells us that the C naught gate leaves the control qubit X alone, but flips the target if X is set to 1. So this is similar to how the XOR gate works. And what happens is that the target Y is switched to the value of the XOR combination of X and Y if X is set to 1.
Ian,
So
may I ask a
yes,
question?
please.
Uh, the the control and target are found within the CNOT gate.
Yes.
Okay.
Yeah. Yeah. And so you understood this conversion. It's a very
Yes.
simple conversion. Yeah.
Yes. I
And
understood it.
so yeah. And so they had this equation. Um, let me just put one note. Yeah. So they had that equation. This one here. This one in yellow.
Yes.
Uh, X control target is Y, and they say that if X is 1, it flips Y to the XOR combination of X and Y. So what that means is that if for example you looked at if you looked at, for example, um, say 0 and 1. Okay. um, okay, let me say 1 and 0. Okay, so this is X and this is Y. Okay,
Yes.
which is this one here. So the XOR combination of this is 1. And how does XOR work? XOR works that if both are different, it gives you 1. If they are the same, it gives you 0. That's a brief description of how the XOR gate works. So the XOR combination of 1 and 0 gives us 1. And so if the control qubit is 1, it flips the target, this one here, to the XOR combination of 1 and 0. Yeah. And so that is the equation here. Yeah, this equation. Okay, so let me go back to the slide. Okay, yeah, and okay, so to wind it up, they say it can also work on a 3-qubit system. And here you can see we have these 3 states in this gate notation. So the CNOT gate is a classical gate, but it can be combined with single
Yeah.
qubit gates to do, yes,
Previously, when we had two values within the Kate symbol, that was
yeah,
the 2-qubit system.
yes, that is a 2-bit system.
So this is a 2-bit system.
Yes,
Yeah.
this, for example, this equation 2-bit system. And previously, earlier on in the other classes, we covered single bit systems. We had Ket 0 and Ket 1. Those were single bits.
Okay.
Yeah. So yeah, at the last slide, they're saying that it can work on a 3-qubit system, and this 3-bit system is represented by, for example, this. And here they're saying the CNOT gate is a classical gate, but it can be combined with single qubit gates to do non-classical things like entanglement. So in the next video, um, actually I want to record it separate, showing how entanglement happens. Yeah, and they're saying it's when it's combined with other gates, you can produce an entangled state. So we didn't prove that here, but I'm going to provide a video showing how entanglements created with the help of the CNOT kit.
Okay.
Yeah, thank you. That's what I had. Thank you for the questions as well.
So just a quick recap. So far, we have looked at the CNOT gate, then the Hadamard
Yeah,
gate, and which other have we looked at any
yeah.
other gate?
The first gate was the NOT gate.
The NOT gate.
Yeah,
NOT
and
gate.
so in the next, yes, NOT gate. The NOT gate is the classical gate for the NOT gate is the inverter. So it just flips the state. If you have state 1, it flips it to state 0. Yeah, then the second gate, the Hadamard was for it created a certain state. It was the gate before this one. And then we have done this. Then in the next week we shall look. I want to finish the gates. I think there are 2 gates left, which is mainly the Toifili gate. Yeah.
Okay. If I have any more questions, I think I'll ask you via WhatsApp. And today I was asking a lot more questions because today it's only you and Tracy who have presented, so we had enough time. So yeah, thank you for presenting. I think we can stop here today unless there's something else we need to discuss.
Right. I think we can end here.
Nice weekend.
Have a good weekend. All right.